Okay, good morning everybody, time to start. So before I start, an announcement. This is not the day that you have to wear the t-shirt. Okay, I got confused, it's on Saturday, actually for the excursion. Okay, but whatever, I use it 2 days, it's not a big thing. Okay, that's the first thing. So the second thing, actually I want to finish with the last things that I wanted to tell last day. So maybe you read them because they are already in the lecture notes that I gave you. And you can use it for the exercise, but anyway, we're going to see it together. I already wrote it in the blackboard because, I mean, it's kind of hard to write in the blackboard, so in this way it's already done. I can go faster, okay? So, I mean, if you remember, last day I told to you about this dual code, okay? But I didn't give the definition. Okay, so now I'm giving the definition. So the idea is that we start with a code that is an NK code. So do you remember the N is the length of the code? So the code is going to be a vector, and the number of coordinates is going to be equal to n. And k, well, is the dimension when you have a linear code. So when you have a linear code, this is going to be isomorphic to fq to the something. So this something is a k, is a side, okay? Or otherwise, that means if it's not a linear code, that the cardinality of c is q to the k, okay? Okay, so with this in mind, we define the dual code as follows. Basically, what we do is like we take all the vectors in the total space, so fq to the n, such that this condition is satisfied. So c times the transpose, so again, well, equal to 0. Again, here the notation, why it comes from, because I'm looking at the vectors as row vectors. So if I want to do the product of 2 vectors, I need one to be like a row vector and the other one a column vector. Okay, so this is why I'm getting the transpose here. So basically, I'm looking for those vectors that make the product equal to 0 for all c in the code. Okay, but if you remember, what did I do with the top? Actually, we know how to generate all those vectors because we saw a very special matrix last day. It was a parity check matrix. Do you remember? And actually, the condition that we wrote was kind of this thing, right? The condition that we wrote is that for the parity check matrix, we have this thing, right? Where G was a generator matrix of the code. So basically, if you want that C times x to the t is equal to 0 for all C in C, is enough with checking that, I mean, when you take C, the elements of the basis of your, well, of a basis, then this product is equal to 0. So honestly, it's enough with doing G times x to the t equal to 0. But I mean, we have some generators of these vectors, the equations that are satisfied by the code, right? And those ones are the one given by the parity check matrix. So basically, what happens, if you want, is that for the dual code, H, so the parity check matrix of the initial code, the C, is a generator matrix. So if you want, the idea is like associated to a code, you have this generator matrix and you have this parity check matrix. So the idea is that you are defining a code for which you are switching both matrices. You are taking as generator matrix the 8, and we'll see now that as a consequence, you are going to have that the G is going to be the parity check matrix. Okay? And why do you have that? Well, actually, I mean, we have already seen this equality, but I mean, starting from this, now you can get a transpose in both sides of this equality, and then what you get is like 8GT is equal to 0. Which means that if you started, well, with a code, the dual code, that has 8 as a generator matrix, then the G is the parity check matrix that corresponds to the 8. Okay? So we have a clear definition of the dual code, and we know how to construct it now. Okay? So let's look at the parameters of the dual code. Okay? So what I say in this proposition is that actually the parameters of the dual code are those ones. It is an n minus k code. And that actually the dual of the dual is equal to the original code. Okay? So let's prove this. So proof. I brought, yeah, sorry. So basically the idea is that we know that the generator matrix of the dual code, as we said, is this 8. And this 8, I recall, is a matrix that here has length n, and here has length n minus k. So basically here we have the answer, right? Because for 8, that is going to be a generator matrix of the dual, I have vectors of length n. So the length of the code is going to be n, right? And now how many vectors do I have? N minus k. So the dimension of the code generated by this generator matrix to have dimension equal to n minus k. Okay? So in this way we proved this thing about the parameters of the code. Can I say anything about the distance? Actually no, it's kind of difficult. So I mean we don't have like a nice expression or formula for determining which one is the distance of the dual code in terms of the distance of the original code. But well, I mean, at least we have the length and the dimension. Okay? Now, I want to prove that the dual of the dual is equal to the original code. But this is easy with the characterization that we gave here. Why? Because I'm going to write here generator matrix and parity check matrix. So for C, I have that the generator matrix is G and the parity check matrix is 8. For C dual, I said that I have to switch the matrix. So I have 8 and G. Okay? If I consider the dual of the dual, what I have to do is switch the matrix here again. So I'm getting G and 8. So basically the dual of the dual is a code that is generated by the matrix G, that is the same one that was generated in C, so basically they are the same code. So we have the equality stated here. Okay? Okay, very good. So now of course you want to see like some examples, right? So an example, for instance, an easy one, before I go to a more difficult one, is if you take the two trivial codes, okay? If you take the code 0 and FQ. What is here the generator matrix? Nothing. There is nothing inside. Okay, well, I mean, it's a little bit weird, this is an example, but we have nothing inside. Okay, but what is the generator matrix here for the, to the end? The identity, this we saw, you take like a basis of the whole space, right? So, okay. Here I'm going to write it like generator matrix and the equations, okay? So here what we get is a generator matrix is the identity of side n times n, okay? Which ones are the equations? So the parity check matrix that define this vector space. Actually, no equation at all, right? And here we have no generator. Which ones are the equations that are satisfied by this vector space? All of them, because I have a vector, so every equation holds. So basically I need all the possible equations. So a basis of all possible equations, again I can get the canonical basis. And basically I get the identity. So I know that this example is maybe a little bit unnatural because you don't really have anything here, but we're going to see now a more natural example for the dual, okay? And for this, I'm going to define like the generalized Hamming code. So, I mean, if you remember, we were talking a lot about the Hamming code with parameters 7, 4, 3, okay? So now I'm going to give a generalization of this Hamming code. So this generalization, you take n equal to something that you can write like this. I mean, notice that this is really a generalization about what we have, because we have q equal to 2 for the Hamming code that we saw. So basically here you are not dividing by anything. And here we have a 7, but 7 is 8 minus 1, so 2 to the 3 minus 1. Okay, so if you want, our special code was with q equal to 2, r equal to 3, n equal to 7. Okay? Okay, so to these parameters, we are going to construct this matrix. Okay? So this matrix is not well defined in the sense that it's not uniquely defined, but you just take a matrix with the properties I'm going to describe, and wherever the one you take, they are going to generate the same thing. Okay? So the idea is that you take a matrix of side r times n. Okay? Again, look who is n. Okay? In such a way with entries over fq, and in such a way that you are not taking a column that is all zeros, so you always have to write something. Okay? And on the other hand, you don't want two columns to be linearly dependent. So you don't want to add the same information twice. Okay? So you do this, and you define this matrix. Okay? So now, with this matrix definition, you are going to define the code. Where is it? HRQ, that is called the QRE Hamming code. As the one that has the previous matrix that we have defined as parity sec matrix. Okay? So, for instance, in our example, if you want to get an idea of what we're getting, so in the example that we saw, we have q equal to 2, r equal to 3, n equal to 7, as I said, okay, with the parameters that we have here. So basically what you're doing, and you need to take this matrix of side r times n, so 3 times 7, okay? Basically what are you doing? You are getting all the possible vectors that they are non-zero in any order. So let me check that I'm doing right. Oops. And actually, the matrix is somehow well defined up to permutation of the columns, and if I multiply a column by a constant. In this case, because q is equal to 2, I cannot multiply for anything that is non-zero, but imagine that q is equal to 3, then I could multiply one of those columns by 2. Okay, so if you want, the idea is that you generate the same things with the columns. I mean, all the columns generate the full space. So if you want, the idea with this is that independently, so I mean, even if here the definition of the matrix is not very precise, that you have like some freedom to choose the matrix, at the end, the code that you generate by taking this matrix, so again, I mean, for this QRE Hamming code, this is going to be the parity check matrix, okay? And I mean, you can check that this is the parity check matrix for the Hamming code that we saw, okay? So, I mean, at the end, the code is well defined, okay? And now, we define SR to the Q, the QRE simplex code as the one that has the same matrix that we took, but a generator matrix. Okay, so now you have the definition of this code. There is an exercise in the exercise sheet about these two codes. But now, I mean, this gives to us like an easy example of dual codes, right? So proposition, or I mean, actually a remark is very easy. These two codes are dual. Can anyone tell me why those two codes are dual? No? Okay, it's very easy, you don't want to answer. So I mean, these two codes are dual because basically we have the same matrix that for one is a parity check matrix and for the other one is a generator matrix. And this is what we said that happened with the dual code, right? That we just have to permutate the two matrices, the parity check and the dual one, okay? So we have the same generator matrix for the parity check matrix of the other one, so they are dual, okay? Very well. So now I want to introduce another type of code that actually we are not going to use them a lot, well, for one exercise, but I mean, it's funny. I mean, it's part of the history of the code, a famous code that was used. Now I'm going to tell you why it was used. So the codes I want to talk about now, they are called Golai codes. So they are funny because actually they were used for sending pictures of the space to the Earth. You know, when they send like some satellites or to the space to get image. So in particular, there were the ones, the Voyager 1 and Voyager 2 that the NASA sent to the space to take pictures of the space. So, I mean, you know, imagine that you are there in the space, you are taking pictures, and you want to send information to the Earth, okay? So again, you have a channel, you send information, you send the bits. So the picture is made of different bits, okay? So you send this information. But at the end, you want to get like more or less a good quality picture, right? But the problem is that when you send it, of course, this is like an example that there is a lot of noise because you are sending the picture from really far away, so like many things may happen. So this is a standard case in which you want to use a code. So you want to add some redundancy to have like this extra information, so even if you lose some information in the way, at the end you can recover the image, okay? So basically at the beginning they were sending pictures in black and white pictures. So you don't need that much quality, let's say, because a bit is black or white, that's all. So in this case they used a code that was something that was called Hadamard code, okay? But those ones at the end, they were not powerful enough for sending like color pictures. So these Golai codes I'm going to talk now about, they were used for this. So again, another application of those codes. So there are two famous, well, three famous Golai codes. So they are the G24, that is a 24, 12, 8 code, the G23, and Q equal to 2. They are binary codes. And this one, that was a 23, 12, 7, 2 code. So those codes, they have like a special properties. For instance, one of the special properties is that if you fix the length and you fix the dimension, then you get the biggest possible distance. So this is good, right? I mean, we agreed last time that somehow what we look for in coding theory is to, well, if we see from the Hamming point of view, what we want is to construct code that given a dimension and a length, you have the biggest distance. Why? Because this bigger distance is going to allow you to detect more errors. Okay, so this is good. So these two codes, they have like this property. How to construct them? It's kind of difficult, and I mean the length is 24 and 23, so I'm not going to start to write here vectors of length 23 and 24 because it's a lot, but I mean I can say that for this one, the G23, actually it's what is called a cyclic code. So we are going to see this next week, how to construct cyclic codes. And I mean, this construction allows you to describe codes very easily. So I mean, you still don't know the meaning of this. We will see it next week. But I mean, just for completeness, I want to give you the code, not just saying that it exists. It's the one that corresponds to this polynomial. And next week, we will see the meaning of this. Right now, I know that this doesn't tell you very much. But Well, at least I'm saying, okay, you can construct it, and you can construct it by using this. And what do you do? I mean, for constructing the G24, actually you just add a new coordinate in such a way like a parity check symbol, as we did. Do you remember with the Spanish DNA? That was like the first example that I gave you. So you just add another symbol at the end in such a way that equation is satisfied. So basically that means that the dimension is the same thing because it's given by an equation. And you are adding one extra coordinate, so this increased by 1. Okay? And then the distance, in this case, happens to also increase by 1. Okay? So these two codes are also famous because they have a big automorphism group. So I'm going to say something now about the transformations that you can do with the code. And they have as automorphism group, even if I'm not giving the definition, huge groups. They are called the Mathieu group N23 and the Mathieu group N24, those two ones. So those ones are not given them explicitly, but they are huge, like really, really huge groups. Okay, you know, this classification of sporadic groups that they have like weird properties. So those two guys are in there. So I mean, these two codes, they have nice properties. And then Golay also introduced, because those two codes are binary, and there is also a Golay ternary code. Okay, and this one is funny. I'm going to say a few words about it. So this ternary code is a code with these parameters. So again, it's a especially good code in the sense that if you fix the length and you fix the dimension, this is the greatest distance that you can get. So I mean, in this sense, it's also a good code. It's a ternary one. And I mean, this code was also discovered by Golay, but was also discovered at the same time by someone else, independently. This someone else was a guy that used to bet, you know, those pools that they are like football match, and you have to guess the result. So you say like, you write a 0, 1, or 2, okay? For a match, you try to guess. A 1 if the first team wins, a 2 if the second team wins, and a 0 if they're tied. So they are like these competitions that you get like a list of matches that they are going to be played during the weekend. And you have to bet which one is the result. And if at the end you get like all your guesses were right, except let's say 1 or 2, then you get a prize. So it was a guy that was playing to this kind of games. So basically at that moment there were like 11 matches, and you wanted to have at most 2 errors. So what was the idea to, I mean, this person, what he wanted was like to give like a lot of bets, but in such a way that he always could win. So how do you do that? And actually codes are an application for that. Why? Because I mean, if you look at this code, it's length 11, so the number of matches that were going to be played. The minimum distance is 5, which means that you can correct until 2 errors, okay? So this means that basically you take your code. Okay? So your code are those points. So basically your points here in the code are going to be the bet that you do for the matches, okay? Because each point here is a vector with coordinates 0, 1, or 2. So it's for the match I in the ith position, the result that you think you are going to have. So you bet for all those results, okay? Now the matches are played. So we have the real result, okay? The real solution. And we get something like this, okay? But now because the minimum distance is 5, okay, the distance between any 2 elements here, that means that this result will be within a distance at most 2 from one of the points that I took in my code. Which means that one of your bets had at most 2 errors. So you are getting the prize. So this person that was betting in this kind of games actually rediscovered like this code in order to win the prize. You know, and actually it's funny because when I saw that, I thought, you know, I mean, in Spain nowadays, we also have like these games that you can bet about the result of the matches. So, I mean, I took the result when I was preparing my course. So, well, I mean, you cannot see it, but I mean, it's the result like the football matches that we're playing. And I was thinking, oh, maybe we can use this to win in this Spanish game. And I mean, of course, they hire like some mathematicians and check that even if you are clever enough to use like those codes, you are not going to win. So, you know, like in average, you lose money. So, I mean, it's not a for sure you win game. And, well, I mean, in Spain, actually, how did I check it? Instead of 11 matches, you have 15. So I will need a code of length 15, okay? Now the dimension, I don't know. Of course, the smaller the dimension, the best, because that means that you have to do less bet. I mean, those are the points in the code. These are the bets that you have to buy the ticket, let's say. And then here, the minimum distance. So the minimum distance, in my case, I want it at least with the same thing. At most, I can have 2 errors if I want to win. So if I want to correct 2 errors, I need distance 5 at most. So basically, the idea is that if you want to know now how many tickets you have to buy, it's going to depend on the game. So basically, what I'm looking for is for a code of length 15 with minimum distance at most 5, and I want to minimize this case, okay? So now the funny thing, I'm going to give you in a few minutes now like some links in where you can find like a website with a lot of tables of codes. So you can look at those tables and you can find which one is the minimum k. And in this case, the minimum k that I found was k has to be greater or equal than 8, which means that you have to buy 8 to the 3 tickets. And if you have to buy those tickets, you look at the price of the ticket, you look at how much money you get with the price, and you realize that it's not worth it, so don't play. Okay? But, I mean, even if you really like play, because, yeah, we have something, it's like, okay, in this way it's not working. But, I mean, if you look at the matches that were going to be played that day, so, I mean, I guess some of you like football, and something we are good, or we were supposed to be good in Spain, was at football. And I guess that you know Real Madrid team and Barcelona team. So, I mean, they were not playing one against the other. So you can assume that both of them are going to win with the other people. So in this case, I mean, if you're assuming that Barca is winning and Real Madrid is winning, okay? So in this case, instead of looking for 15 matches, you have to look for 13. And same thing. So you look at the tables that you have with all the codes, and in this case, you get that k has to be, you can get k, what is it? What is it? Okay, now I don't find it. Oh, yeah, 6, okay? And if you do this, if you take, no, sorry, 7. If you take this, instead of doing 3 to the 8, have to do 3 to the 7. You take the amount of money that costs its ticket and the price, and in this way, you win. But the problem is that you are assuming that Barcelona and Real Madrid are winning, which is, well, kind of realistic, but you cannot be 100% sure. But okay, so this is another application of codes. As you see, you can apply them for many things, like stupid things as betting games, but you can also apply it, I mean, this same like code for things as sending pictures from the space. Okay? So there you have more applications. Very good. I wrote, I mean, in the notes that you have in the internet, I wrote more stuff. I don't really have all the time, but what is important that I want to mention is the meaning of 2 codes to be equivalent. So I'm going to write this definition, because somehow you need to use it here, okay, for checking that those codes are well defined. So I'm just going to give the definition for this. It is here. So definition, we say that 2 codes, so I'm going to call them C and C prime, and we write it like this, are equivalent if and only if there exists M, well, I'm going to call it phi. Phi, an isometry. I'm going to define now what it is an isometry. Such that the image of one code after the isometry is equal to the other. So an isometry here is basically a map that goes from FQ to the N to FQ to the N, okay? Such that, this is the nice property, the distance between the image of two elements is equal, taking another chalk, to the distance original two elements. Okay? So I notice that I'm not asking extra information in this file. I'm not asking it to be linear, for instance. I mean, this is just a map. Even if here we have vector spaces, this is just a map from one set to another one. And I ask this condition, that the distance in the first space is the same one that the distance of the image in the other space. Okay? So now I say we define two codes. We say that they are equivalent if they satisfy that there exists an isometry from one to the other. Okay? So we can see an example, for instance, a very easy one. If you take, for instance, this code, well, the code given by this generator matrix, 1, 1, 2, 0, 1, 1, over F3, okay? So is the code generated this vector and this vector? So, I mean, it's easy to check that the code generated by the generator matrix is equivalent to this one. What I did here, I just permuted the columns. So if you want here the isometry, is that I send the first vector to the second one. So I mean, in this case, this isometry that I'm saying is linear. It's just given by a matrix, okay? What I'm just doing is that I'm sending this vector to this one to this one. So in this case, it's a and then a linear combination of these vectors goes to the linear combination of the image, okay? So I extend the map by linearity. And in this case, this is an isometry because I'm sending a vector of weight 3 to another vector of weight 3. Okay? The same thing with this one of weight 2 and this one of weight 2. Okay? Very good. Now I'm going to the next thing. What is it? Oh, sorry. I forgot. I have to take something back. So now I want to discuss a little bit about construction of codes. Sorry. So, I mean, we have seen that a code is given by a generator matrix, but I mean, in general, we would like to construct codes in another way, okay? So to have different ways of constructing code. So, I mean, in the exercises, this I leave it as an exercise for you. I give like different ways of constructing codes. You will also have like the constructions in the lecture notes that they are going to be online today or tomorrow. I have to send them. Okay, so you can check like all the things I'm saying. So for the construction of code, I'm not saying very much right now. Okay, so I mean, this you will see it in the exercise session. But I mean, some easy ideas that you can see. There is something, for instance, that is called puncturing. That this is, you get a code like here, and for instance, I forget one of the coordinates, so I'm puncturing the code. So imagine that starting by this code, I forget this. So I'm just working with the code that is generated by those vectors with less coordinates. Okay, so this is a way of creating a new code starting from an already existing code. Okay, so in the exercise session, you are going to see like different ways of constructing codes. Okay. And this is useful. Why? Well, I mean, in the exercise session, you are also going to compute which ones are the parameters of the code, of the constructed code, starting by the parameters of the other code. So I mean, if you want, we have already seen a method here that was starting from a code, you can construct the dual. This is a new code, okay? And we gave like the parameters conditions. So here in the exercise session, you're going to do the same thing. Starting with some code, you're going to construct new ones with new parameters, okay? And why is this interesting? Being able to construct new code. So this is interesting because, again, I'm repeating myself, but because it's like the important thing. It's like from the Hamming point of view, what do you do in coding theory? You want to construct codes with good properties. Because later you want to use them for different applications, as we saw, okay? So basically, I'm going to write it again. Normally, what you have, in this case was a little bit different, but it's kind of the same thing, is like you fix and the dimension, and you want to find a code with the maximal minimum distance. So you want to maximize the minimum distance. So, well, I mean, not only is like you want to answer this question, which one is the maximum distance, the maximum minimum distance that I can have, but you want also to be able to construct a code with these properties, right? So, I mean, as I said, there are some tables. So I'm going to give you the, well, maybe it's easier if you look at the note. Well, I give you, one of them is W, W, W. Well, I'm writing only one of them, and then the other one, you can find it in the notes. Code, tables, code, D, E. Okay? So, for instance, you go to this website or to the other one that you will find in the lecture notes. There are a lot of tables of code, what is known, which code you know to construct. And I mean, actually, it's quite cool because you get like a table. So you have here like N and K. So what you get inside is a code, so the value of the maximum minimum distance. And if you click, you can see an example, how to construct a code with this distance. So the first thing is like, do we know to do this always? And actually the answer is no. I mean, in those tables, you're going to find the information that we know. But somehow you're also going to find like so many problems, open problems. Open in the sense that for a fixed value of N and K, which one is this maximum minimum distance? And we don't know. So I mean, like, if you want to start to research, you could start to try to look for those codes that, I mean, we don't know the answer. So I'm going to give you here just for curiosity, or if you want to spend some time working on this, okay? Like if you take, for instance, so this is the first open problem, or yeah, the smallest case for which we don't know the answer, okay? If you take N equal to 32 and K equal to 14, okay, then we know that the maximum minimum distance is something between 8 and 9, but we don't know. So we know it has to be bigger than 8, okay, and it has to be smaller than 9. We know that it has to be smaller. To explain, there are like some inequalities between N, K, and D that has to be satisfied. So one of those equalities implies this 9. So we know that it has to be smaller or equal than 9. We know that it has to be greater or equal than 8 because actually there is a construction of a code with those parameters. N equal to 32, K equal to 14, and minimum distance 8. So I mean at least one with this minimum distance equal to 8. But we don't know if this is really the maximum minimum distance. So what would you have to do if you want like to solve this open problem? Or well, you prove that there is no way that there exists a code with these parameters and minimum distance equal to 9 with some theoretical argument, or the other way around. You prove that indeed there exists code with those parameters and minimum distance 9, and then you have to construct it. So I mean, if you think about it, like these are not very big numbers, right? I mean, when we think about like open problems, and something that a priori you expect that you are going to have like very big numbers, right? But here they are not that big. But well, well, this is a binary code, Q equal to 2. Yes, I think that is, yeah, I'm not saying a stupid thing. Yeah, Q equal to 2. I mean, if you think this is a vector space, I mean the total space of side 2 to the 32. So yeah, maybe it's a big number. Well, I mean, I don't know. I let you the problem, and I let you looking at the website to see at the different information that you can find in the table. Okay, from these tables, I found the values that you have there. Okay, so now the bounds. So yeah, perfect. Today I'm going to have the time for doing everything. I'm just going to mention like, well, 1 bound, 2 bounds, and you have more bounds in the exercise sheet. So bounds, that means like inequalities regarding these N, K, and D, okay? And then I'm going just to do an example. So you can see that these bounds, they usually hold. So the first bound is a very well-known one. I mean, it's a typical one that we see when we study coding theory. That is a Singleton. Bound. Okay? These bounds basically said you start with an N, K, D linear code. Then you have that the minimum distance is smaller or equal. Okay? So first example, we can check that, for instance, for the code that we have here, that I said that exists, this happens, right? Because 8 is the minimum distance for the one that they constructed, is smaller and equal than 32 minus 14, that is 18, plus 1, that is 19. So 8 is smaller or equal than 19, but we cannot say anything else. We cannot rule out the 9 here. Okay, so it's not precise enough if you want. But it holds, it's true. Well, let's prove it. So the idea basically is the following. Look at the parity check matrix, okay? Look at the rank of this matrix. So the rank of this matrix, recall that is an n minus k matrix. So the rank is going to be smaller or equal than n minus k, right? Again, because 8 is a matrix that here you have n minus k and here you have n. So I mean, at most the rank can be this amount. But now, on the other way around, remember the last proposition that we proved 2 days ago? So that gave us the minimum distance in terms of the columns of the matrix 8, if they were linearly dependent or not, right? So basically, the rank of 8 is the number of columns, I mean, give you a number of columns that they are linearly independent, right? So that means that this number has to be greater or equal than d minus 1. Because if it was smaller than this, then you will find like some, with the proposition of the other day, you will get a contradiction with minimum distance. Okay, so this is because of the proposition that we saw the other day. Okay, but now you just have to put all these together, right? So then d minus 1 is smaller or equal than this, that is smaller or equal than n minus k. So you get the quality here. Okay? Very good. Now I'm going to show you another bound that is called the Hamming bound. As you see, Hamming appears everywhere. And I mean, this is also nice to see the proof. So the Hamming bound I'm going to write it and then I explain what means everything. Tells you that P, Q, and T is smaller or equal than A, Q, and equal than D. So, lot of notation. So, what is each thing? So, this one is equal to the maximum of the cardinality, the sign, of a code with parameters n and d. Okay? Any code. And this one is the same thing if I ask the code to be linear. Okay? So this is equal to the maximum when linear of the cardinality of a code with these parameters, n and d. Okay? Here you have q to the n, and here what you have is the volume. This is to the volume radius, this number, in a space of dimension n, f q to the n. Okay? So you get this equality. Why? And here the proof is nice. Imagine that you have a code, okay, and f q to the n. So I have here all my points, okay? I'm going to consider the bolts of radius d minus 1 divided by 2, okay? So this distance is smaller than half the maximum distance, which means that if I consider those up, because the radius is smaller than half of the minimum distance. Okay, how many points do I have here? Let's say, well, for any code. Q to the k, okay? This is the side. So, I mean, this is the number of points. So, Q to the k times the volume of each of these balls, okay? So, it's what I don't write the parameters, you know which ones they are. This is smaller or equal, since it doesn't overlap, that the number of points in the whole space. So Q to the n. So basically now if I divide by BQ here, I get the equality here. And then, I mean, this is clear because here I'm considering less objects. Those ones are linear. Those ones are linear and not linear. So here you have more things. This is bigger than this. So here you have this equality. I have like 1 minute. So in this last 1 minute, I'm just going to give you an example of a code. We'll see that these two bounds are satisfied. So for this example, I'm getting a particular code, an easy one. Again, I'm going to give it with the generator matrix. So example, I take G given by this matrix and define over F5. Okay? So this Singleton bound here tells us that the distance is smaller or equal than n minus k plus 1. Here, n is equal to 5 because I have 5 coordinates. K is equal to 2 because I have 2 rows. Okay? You can check by hand that D is equal to 4 if you compute all the elements. And then what you get is like here, that 4 is smaller and equal than 5 minus 2 plus 1, which is true, and we get equality. Okay? And now for the Hamming bound, what we get is that 5 to the 2, that is the side of this code, because it's the q to the k, is smaller or equal than, so I'm looking at this inequality, okay? So 5 to the 5 divided by the volume. The volume is an exercise to compute this volume. So I'm not giving you the proof of how to compute this volume. We'll see it in the exercise section, okay? But if you use that formula, you get that this value is equal to 21, okay? So if you want to check that this is true, I can multiply 21 here, divide by 5 to the 2 on both sides, and basically this is equivalent to say that 21 is smaller or equal than 5 to the 3, which is clearly true. So both bounds hold for our code, okay? Okay, so we stop here for today. So do you have any questions? Yes? Is
there a way that the inequality of two bounds is equal?
Sometimes it happens to be equal, yes. So it's a nice example exercise. You can try to find one. No, I mean, for instance, in this case, it is not equal. I mean, actually, this number is very much bigger than this one. So it's not a good bound. But I mean, if you go to the notes, actually, there is like a graphic. In the lecture notes, you can see it with, I mean, like a measure of how good are those bounds. And actually, in general, like for big code, let's say when the parameters go to infinity, this Hamming bound is better than the Singleton bound. Okay, but well, I mean, at the end, it depends on the particular example that you take. More questions? Well, so see you tomorrow.